Welcome back. Last video we have seen Fourier integral theorem, and which we have given not so rigorous proof, that means some kind of intuitiveness we have involved in the proof of that theorem, and we defined what is Fourier transform and its inverse transform, and also we rewrote the Fourier integral theorem when the signal, the non-periodic signal or the function fx on the full real line is even function, or when f of x is given only over 0 to, when your signal is given only from 0 to infinity, if you extend that as a even function from minus infinity to infinity, then in that case you can define Fourier. So, your integral theorem becomes in terms of cosines, you can write it as a cosine functions, and through which you have defined what is Fourier cosine transform and its inverse transform of it. So, today if we will just consider in this video we will look at if f is even, if f of x, the signal is odd function in minus infinity infinity, or f of x is defined over x belongs to 0 to infinity, and this we extend as odd function. If your signal is given only from the positive side, you extend as an odd function over minus infinity to infinity. In that case what happens? Then you look at the Fourier integral theorem. So, if you look at up to here, so if you look at this is true. If you look at this part, if f is odd here, what happens to this part? If f is odd, this dt integral f of t into cos xi t, f of t is odd, cos xi t is even function. So, f of t into cos xi t, so you can do the same thing. So, like here, so 0 to infinity you have cos xi x comes out, you have minus infinity infinity f of t cos xi t dt d xi. So, this part, because f is odd function, cos xi t is even function, together this integrand is odd function. So, that makes it, this is 0. So, you have this part is 0. So, this contribution is only coming from the second term now, if f is odd function. So, if f is odd function, we can write from the Fourier integral theorem, we can write f x, or its average part is actually 2 by pi 0 to infinity minus infinity to infinity 2 by, what do you have, 1 by pi, it is 1 by pi, it is not 2 by pi. So, minus infinity to infinity f of t into sin xi x sin xi t. From 0 to infinity integral f of t sin xi t dt sin xi x d xi. Now, from this you can define what is called Fourier sine transform. Definition is, we define now f s, this is the definition of xi. This transform is over a function signal f of x defined over 0 to infinity, and this is by definition is if I take it from here, this part with root 2 pi, split root 2 pi here and we put 1 by root 2 pi. So, 2 pi by I split it into root 2 pi into root 2 pi. So, then you can take this as our definition, 2 by pi 0 to infinity f of t sin xi t dt. So, this is your Fourier sine transform and Fourier inverse transform, inverse Fourier transform, inverse Fourier sine transform. And this is you can get back your signal, that is f of x, that is directly from Fourier integral theorem. So, what you have is 2 by pi. So, this whole thing is integral 0 to infinity, this whole thing is your f s of xi, and you have sin xi x d xi. So, this is your inverse Fourier transform. So, if this is your definition, this is the fact from Fourier integral theorem. So, inverse transform is always like in the, like earlier, even for Fourier series, you have defined only Fourier coefficients, and the fact that every signal you can decompose in terms of you can compose in terms of these coefficients and fundamental signals, that is actually inverse transform. So, here on analogous to that, what you have is you have a definition of Fourier sine transform, and the Fourier integral theorem is actually giving you this inverse transform. Okay. So, like this you can define your Fourier transform and Fourier cosine and Fourier sine transforms. Okay. So, this again I stress here that Fourier integral theorem, either cosine part or sine part, Fourier integral theorem is only it is not rigorous proof that I have given. So, we will eventually see the rigorous proof of that when f is the signal is non-periodic function or the signal is piecewise smooth function. So, in that case we will actually show the Fourier integral theorem in a rigorous way, and then we can mathematically that gives the completeness that we can believe Fourier integral theorem completely. You can understand that proof in the later videos. So, we will do some examples now. So, if f of x is, if you take it as 0, if x is negative, such a function is you have to choose this e power minus x, x is positive. So, if you are using this non-periodic function which is defined everywhere, because you are dealing with the integrals in the Fourier transforms, you are dealing with the integrals. So, at one point you need not define, it does not matter what you define, okay. But if you define here some value at x equal to 0, so that should be that you will see exactly what it is here, okay. So, we will see at x equal to 0 whatever you can define, okay, but then it should be on par with the Fourier integral theorem. So, if at x equal to 0, it has to, what is the limit of f of 0 plus f of 0 minus divided by 2, average value as limit x goes to 0 side, this is e power minus 0 is 1, and this 1 plus e power negative side is anyway 0 divided by 2, so it is half. So, its value should be on an average, it converges to fx is Fourier integral value is actually converges to half, okay. So, if you think that it is if even the average value at x equal to 0, it has to converge, so it has to be half here. So, it does not matter. So, let us not give any value here. So, we will see what exactly, if it is given here is a half at x equal to 0, we will see, okay. Still it is a discontinuous point, you still give the value. So, the Fourier integral theorem converges to is actually equal to f at 0 at x equal to 0, that is the average value of this side and this side, that is also that is half, okay. Otherwise you need not even define. So, if such a thing, what happens to this this function, then f of x is piecewise, it is piecewise smooth function, clear, right. So, these are in terms of elementary functions and absolutely integrable, it is absolutely integrable. So, integrable over minus infinity infinity, piecewise smooth function on every finite interval, because it is smooth anyway less than 0 on positive side, only discontinuity is 0, and that is where you have e power 0 is 1. So, it is going to be a jump of 1, the jump is 1. So, it is actually piecewise smooth function in every finite interval. It is also absolutely integrable over a full real, and because integral minus infinity infinity f of x dx is actually equal to 0 to infinity e power minus x dx, which is finite. That is why it is absolutely integrable, okay. And what you have, and you have by Fourier integral theorem. So, these are the conditions of Fourier integral theorem, intuitive proof we have given in the last video. By Fourier integral theorem, what we have is f of x, or at discontinuous point f of x plus, we have only 0 point here, okay, x plus or f of x minus divided by 2, which is equal to what you have. So, you have 1 by 2 pi minus infinity infinity minus infinity infinity f of t into e power minus I xi t dt. This is your Fourier transform 1 by root 2 pi, 1 by root 2 pi comes out, and that is e power I xi x d xi. So, this is exactly from your Fourier integral theorem or Fourier transforms. Okay. So, you try to put this f of t value that is given here, e power minus t as x positive. So, what you get is 1 by root 2 pi minus infinity infinity, and you have 1 by root 2 pi. This is from 0 to infinity e power minus t and into you have if you combine with the exponential of e power minus I xi t, you have 1 plus I xi dt into e power minus I xi x d xi. Okay. So, this is equal to 1 by root 2 pi minus infinity infinity 1 by root 2 pi, and this value is 1 by 1 plus I xi. So, e power minus of e power minus t 1 plus I xi, and this if you do from 0 to infinity to limits, this because of e power minus t, this is going to be 0 at infinity. So, this minus or minus plus e power 0, that is 1 divided by 1 by 1 plus I xi. So, you get, when you do this, you get this part into you have e power I xi x d xi. This is equal to, you can rewrite, so you can write this as 1 by 2 pi, and you have a minus infinity infinity. Now, you can write e power exponential function e power I xi x as cos xi x plus I sin xi x divided by 1 plus I xi d xi. So, how do I make this real part? Take this as a real part and imaginary part. If you do this, you can write 1 by 2 pi minus infinity infinity, and you try to rewrite this as you multiply and divide with 1 minus I xi. So, that the denominator will become 1 minus I square xi square, that is 1 plus xi square. I is a complex number, which is I is root minus 1. So, you have 1 minus I xi, I multiplied, and denominator I multiplied, numerator and denominator. So, you get this one, and cos xi x plus I sin xi x dx d xi, and this is a real part. If you look at it, cos xi x, imaginary part is plus xi sin xi x divided by 1 plus xi square d xi plus I by 2 pi minus infinity infinity. I part, you have a minus xi cos xi x minus, this is going to be plus sin xi x divided by 1 plus xi square into d xi. But if you look at this second integral, this integral is xi cos xi x is odd function, sin xi x is odd function. So, the numerator is an odd function, denominator is even function. So, together it is an odd function. So, this part is 0. So, you have is 2 pi minus infinity infinity cos xi x plus xi sin xi x divided by 1 plus xi square d xi is your f of x, or it's if it is continuous, this is f of x, otherwise this average value if it is at this continuous point, right. So, if you choose xi equal to 0, that is the singular point for this function, right. What is your function? F of x is 0 if x negative, and e power minus x positive. So, you have a 0 is a singular point, this is 0, and what you have is e power minus x at x equal to 0, it is 1. this is the jump here. So, this part, okay, and it is actually going to 0. So, it is coming to 0 like this. This is the function you have, asymptotically it goes to 0. This is your f of x. So, 0 is the only discontinuous point with the jump. So, you because of that you consider left hand side f of 0 plus, that is 1, plus f of 0 minus, that is 0, and you have by divided by 2, that is actually half, 1 plus 0 by 2, which is half, which is equal to 1 by 2 pi, and you have minus infinity infinity. You put x equal to 0, cos xi x is 1, and if you put sin xi x, x equal to 0, this is 0. So, you have d xi by 1 plus xi square. Okay. So, you expect this to be 1 by 2. Is this really true? That means, this is, if you actually calculate this integral, you have 2 pi pi, and this is tan inverse xi from minus infinity infinity. So, what you get is 1 by 2 pi, this is pi by 2 so, this is tan inverse infinity is sin pi by 2. So, this is pi by 2 minus minus of tan inverse of minus infinity is minus of minus pi by 2. So, it is actually 1 by 2 pi times pi. So, it is 1 by 2. So, this is actually matching, you can easily see that. Okay. So, this is actually true. So, Fourier integral theorem for this example you have seen that is true. So, now you can define your function like this at x equal to 0, it is actually half. If you define like this, then you do not have to consider this this part. So, it actually converges to f x. Now, so then if I define like that, f of 0 is half at x equal to 0, then you can simply safely write f for any other point, it is anyway converges to that value is converges to f x. So, you can say that f of x is actually equal to 1 by 2 pi minus infinity infinity cos xi x plus xi sin xi x by 1 plus xi square d xi. This is true for every x from minus infinity infinity. This is what we can see from the Fourier integral theorem. Okay. In the same way, we can also will do some more example. We will in this case we will try to show that exponential e power minus x cos x, show that this is actually equal to 2 by pi 0 to infinity xi square plus 2 cos xi xi divided by xi square plus 4 d xi. Can you show that this integral value is equal to e power minus x cos x? So, we will use the again we will use so you can clearly see that this is a continuous function. So, this is true for every x in minus infinity to infinity. Again we will try to use Fourier integral theorem for this function. Okay. If you do that, use Fourier integral theorem for this function over a full real line, or because this function is if you try to do that. So, if you use that, you want if it is only for positive side, only one side if you want to use, you can use Fourier cosine because you want only from 0 to infinity. So, you expect you want to use the Fourier integral theorem in terms of cosines. That means, it is valid only for x positive. So, if you cannot give x negative side, okay. For all x you cannot give. So, if I give x positive, I can safely write the Fourier integral theorem in terms of is only positive side. So, clearly f of e power minus x cos x is only one side is defined, minus x cos x is equal to, you have 2 by pi is actually you have like this, you remember like this, you have 2 by, this is inverse transform. Now, they have a transform cos xi x d xi, that is what it is. So, you here inside 0 to infinity f of t, that is e power minus t cos xi t dt. This is by Fourier integral theorem for every x positive. So, this is 2 by pi 0 to infinity. Now, if you look at this integral 0 to infinity e power minus t, and this cos together cos t into cos xi t, you can write it as cos sum plus cos difference. So, you have a cos 1 plus xi t plus cos 1 minus xi t or xi minus 1, cosine does not matter, both are same, dt cos xi x d xi. This is for x positive. So, you have 2 by pi 0 to infinity. Now, you try to expand this, evaluate this integral 0 to infinity e power minus t cos x t dt. This is actually equal to 1 by 1 plus x square. So, you can do the integration by parts and try to bring back the same integral and try to. So, if you use the integration by parts, you can easily see that this value is this. So, I am directly writing. So, you have 1 by 1 plus xi square, x is 1 plus xi, plus the other part, this part we get 1 divided by 1 plus 1 minus xi whole square. This dt integral is over. So, you have a cos xi x d xi for x positive. So, you just do this, what you get is this is going to be 2 plus xi square plus 2 xi into this one 2 plus xi square minus 2 xi. So, that is 2 plus xi square whole square minus 4 xi square. Right. Now, simply take this sum this one, what you get is 1 by 1 plus xi whole square into 1 plus 1 minus xi whole square, and here you get 1 plus 1 minus xi whole square plus 1 plus 1 plus xi whole square. So, this is equal to, this is what is integral 0 to infinity. So, let us work out what this is. This is equal to this is as it is. So, you have numerator will be 1 plus 2 plus 2, that is 4 plus 2 xi square, 4 plus 2 xi square, and you have a minus 2 xi here and this is a plus 2 xi, that get cancelled, divide by, and here this is going to be 1 plus 1. So, that is 2 plus 2 xi, 2 plus xi square plus 2 xi, and here 2 plus xi square minus 2 xi. So, you get xi square plus 2 into 2, this 2 here you get 2 plus xi square whole square minus 4 xi square. So, what is this one? You get 2 plus xi square a plus b minus a minus a square minus b square. So, what you end up is xi square plus 2, so not getting here, what is this, divide by, this is going to be 4 plus xi power 4, this is going to be 2 to 4, 4 xi square minus 4 xi square, yeah, this is fine. So, this is going to be 0. So, if you see this one, so 2 by pi integral 0 to infinity, this is what it becomes, cos xi x d xi x positive, and here as well this is equal to 2 by pi integral 0 to infinity cos xi x d xi, and this is actually 2 by pi integral 0 to infinity cos xi x. There is something when I do this sum of the causes, if when you replace this, you should have 2 times, sum of this is 2 times, so this is going to be 1 here. So, this is actually 1, that is a mistake. So, this is 1, and you have what you have is simply 1. So, you finally get 2 by pi integral 0 to infinity xi square plus 2, here anyway cos xi x d xi. So, this is by 2 comes out cos xi x d xi divided by, and this is going to be, if you expand this, and you can see that xi power 4 plus 4. Okay. So, this is for x positive. So, actually, so this is there is something wrong in this typo, it should be x power 4, xi power 4, this is the correct problem, should have xi power 4. Other if it is xi square, this is actually is not integrable, if it is xi square. So, you see this xi square is like order of 1 cos x, so it should be x power 4 xi, and it is 1 by xi square order. So, it is integrable and its value is finite here. So, for every fixed x. So, it is x power 4. So, this is the correct thing. So, I have shown now that this integral e power minus x cos x value is this integral by Cauchy by Fourier cosine Fourier integral theorem in terms of cosines. This you can use if your function is even function, or here it is certainly it is not even function or not neither even function nor odd function. But if or in other case when it is defined only one side, you can extend as an even function or odd function. So, I extend as because it is given for x positive, you can extend this as an even function and then use the Fourier cosine integral theorem. Cosine in terms of cosines, you have Fourier integral theorem. So, if you use that, you can show this one. That is how we have done this. Next, I will try to show what is the Fourier transform of a delta function of x. What is the Fourier transform of delta function? Okay. I will show that this is actually Fourier transform of delta function, delta cap of x, that is delta cap of xi is actually, once you have a cap, is a function of xi. So, that is going to be 1 by root 2 pi. So, this is what is the result. We will try to prove this. So, to show this, we will just define what is a delta function again. So, we have seen that delta function by definition should have is infinity at x equal to 0, 0 at x is not equal to 0. So, this I can think of as a limit as epsilon goes to 0, some usual functions f epsilon of x, where f epsilon of x I can think of 1 by epsilon if x belongs to minus epsilon by 2 to epsilon by 2 with closed intervals of course, and then 0 otherwise. you think of them as like this is your definition, and you, because why it is delta function is not a function, you can think this is given as a limit of usual functions f epsilons, which are well defined piecewise smooth functions. Now I can calculate what is my Fourier transform of x, the limit of this Fourier transform. So you have because this function is uniformly continuous functions or minus or as epsilon. So you fix your epsilon as 1 as epsilon goes to 0. So in the neighborhood of 0, because its epsilon goes to 0, because this function is you can think of epsilon equal to 1, and on which all these sequence is uniformly convergent. So uniformly convergence is assured. F epsilon of x, you can look at the limit fx converges to f epsilon converges to delta function. This convergence is not so you cannot simply and you can easily see. So how do I do this? This integral and you see the way we have defined this integral value dx is always equal to 1 minus infinity infinity. Because of this I can define that this integral is finite for all values for every epsilon. So this is finite for every epsilon positive. So in that sense you have convergence is fn of x. So for all values of, so this is minus infinity infinity or minus epsilon by 2 to epsilon by 2, or which this integral is all value is always 1, and what is this uniform convergence is the question. So fn x, or just we will just for later anyway. So we still have a question whether we can do this. So the so this cap, the Fourier transform of this delta function is equal to the limit. So what we do is 1 by root 2 pi, the definition 1 by root 2 pi, you have this integral minus infinity to infinity, limit epsilon goes to 0, f epsilon of x, this is my delta x into e power minus I xi x dx. That is my definition of Fourier transform. So this is 1 by root 2 pi. You think of you can bring this limit outside, and now we calculate this f epsilon of x e power minus I xi x dx. If you do this 1 by root 2 pi so this is what is the question, right. So in this case this limit, when you can allow this limit to go inside this integral, provided this convergence is uniform. So this is f epsilon of x is always bounded with 1, right. So because it is 1 by epsilon, no this is, so we will see the justification anyway later. So if this is still question. So assume that you can do this. So 1 by root 2 pi, and then you have this limit epsilon goes to 0, and this you try to expand. So this is actually given as minus epsilon by 2 to epsilon by 2, f epsilon is 1, right, that is 1 by epsilon. So 1 by epsilon e power minus I xi x by 1 by epsilon comes out dx. So this is 1 by root 2 pi. So limit epsilon goes to 0, 1 by epsilon times, now this integral is by minus I xi, and you have e power minus I xi x from epsilon by 2 to epsilon by 2. So, this is 1 by root 2 pi limit epsilon goes to 0 1 by epsilon 1 by I by xi. Now, I put I by xi, and this is e power you are integrating with respect to x. So, you have minus I xi epsilon by 2 minus e power minus I xi, this is minus epsilon by 2. So, you have this is going to be plus I xi epsilon by 2. So, what you get is 1 by root 2 pi limit epsilon goes to 0 into 1 by epsilon I by xi, this is going to be 2 minus 2 I minus 2 I sine xi epsilon by 2. So, this is 1 by root 2 pi limit epsilon goes to 0 1 by epsilon. So, this you have, this is what you have. So, it is going to be 2 2 by epsilon xi times sine xi epsilon by 2. This is 1 by root 2 xi 2 pi, this limit epsilon goes to 0 or xi epsilon by 2 also goes to 0. What you get is sine xi epsilon by 2 divided by xi epsilon by 2, and this is sin x by x as x goes to 0, that is 1. So, you have 1 by root 2 pi. So, only justification that you have to do is here how you can take this limit from inside to outside. So, this questionable that we will try to justify in the next video. Okay. So, what you have shown is if you take this your delta function, you have shown that this Fourier transform of a delta function is 1 by root 2 pi. Okay. So, this is what is the result. And also in the next video what we see is if you define your Heaviside function, I will define, that is as h of x as it is like Heaviside function is I take 0 for x negative at x positive side up to here it is 0, and when it comes is jump there is a it is 1, there is going to be at every positive side is 1. So, that is Heaviside function. It is 0 if x is negative and it is 1 if x is positive. Okay. Such a thing if you take, that is called the Heaviside function. What we show is delta function that we have defined is actually equal to the derivative of d dx of Heaviside function. In a, see this derivative, so you can see that this is not differentiable at x equal to 0. So, you can think of, so derivative is this side, this is in a generalized sense we have to define, this is the derivative of Heaviside function. We will try to give you a glimpse of what this is. Okay. In a generalized sense, so in a generalized functions, that is a delta function is one such example, you can differentiate this delta any number of times. Okay. So, like that you can differentiate some sense, you can make some sense mathematically. So, in that sense you have a non-differentiable function which is Heaviside function, which you differentiate, what you end up is a delta function. These are, first of all, this is only function, this is the only regular function, this is a Heaviside function is a regular function. You differentiate this itself, it is not legitimate because it is not a differentiable function. So, something which is not differentiable function you are differentiating. So, that means it should be a generalized function, it is not a usual function once what is the derivative. So, that it comes out to be delta function which is a generalized function. I will try to give you give a brief account on this how this delta function is derivative of the Heaviside function, and we know that this Fourier transform of this is 1 by root 2 pi. So, the Fourier transform of this derivative, that is Fourier cap of Heaviside function dash of x, okay, dash of xi. This is 1 by root 2 pi, but I know that this is actually equal to minus I xi. If you calculate, it is going to be minus I xi h cap of xi. So, in that, if you do this, what you see is Heaviside function Fourier transform is Fourier transform of Heaviside function, you will see that 1 by root 2 pi divided by, so this is going to be I by xi, I by xi. So, something like this you will try to see exactly, we will see how it is. So, this also we will see if f of if f cap f derivative, if you want to have, what is this one, this is actually 1 by root 2 pi minus infinity infinity f dash of x e power minus I xi x dx. You do the integration by parts, and by root 2 pi f x e power minus I xi x minus infinity. Assume there is a integrable function f x, absolutely integrable function. So, it has to, at infinity it has to go to 0. So, you end up minus 1 by root 2 pi minus infinity infinity f of x, and you get minus minus plus, this is going to be I xi f of x e power minus I xi x dx. So, this is I xi f cap of psi, it is. So, you have a plus sign here. So, that makes it I xi 1 by I xi. So, it is going to be minus I, this is what you may end up as a Heaviside function whose Fourier transform. We will see, we will try to give you what this all about in the next video. Okay. We will see in the next video with many examples and how to calculate the Fourier transform of these functions. Heaviside function, at least delta function you will have to know because these are very important generalized functions. So, only these we will use only these generalized functions, either derivative of h Heaviside function or delta function whose Fourier transform, how so that we can use them in when you apply the Fourier transform to in the applications, and you try to apply the Fourier transform to boundary value problems in partial differential equations or some differential equation, some boundary value problem when you are trying to solve, you may end up using this Fourier transform on the Heaviside functions or delta functions. That is where it is useful. So, we will see all that in the next video. Thank you very much.